Okay, good morning. So let's get started. Last class we were discussing some basic introduction to real-time communications. We were contrasting it with traditional communication, and then we were looking at its applications, quality of service issues, and so on. So today we will continue from that point, and we will look at few basic issues in real-time communications. So this we were just started to discuss the last time about the traffic in a real time network, and we were mentioning that you will find three main categories of real time traffic. One is the CBR traffic, or the constant bit rate traffic, which is the majority of the traffic in a real time network, and then we have variable bit rate traffic and some sporadic traffic which very rarely arise. The constant bit rate data is generated by several types of sensors, and also the commands to the actuators, they are also in terms of constant bit rate. So over time you see a constant size data is being transmitted on the network. And then we are discussing about the variable bit rate traffic, where the rate of data transmission or the size of data generated by the source, I think that would be more appropriate. The size of the data generated by the source varies at different times. So at some time we have very small amount of data to be transmitted, and some other time we have large amount of data generated at the source needs to be transmitted. The common type of VBR traffic encountered in a network is on-off traffic, where there are fixed size packets generated or nothing is generated. So for some time there will be no data to transmit, it will be idle period, and sometime the data generated by the source is of constant size. Okay, this is the example where the data that is generated by the source is constant, but they arrive very randomly. Yeah, we were just started to discuss that last time about a practical example of such traffic, that is compressed audio signals. Typical traffic that is generated from a audio signal follows this pattern, even video signal. Okay, video signal will be slightly different. To reduce the size of the voice traffic, no data is generated when there are periods of silence, and we were mentioning last time that this is the one of the reason why packet switched voice transmission is effective. No packets need to be transmitted when there are periods of silence, and it is surprising to know that when persons talk, more than half the time it is silent. So this results in on-off sources. Fixed size data is generated during on period and no data generated during idle period. But if it was either a circuit switched or a point to point network, then the entire bandwidth will be reserved for such a traffic. But here the packet switched network, the VBR traffic can be efficiently handled, and that is possibly the reason why we have VoIP etc. becoming very popular and low cost, right. One of the advantages is that no data is transmitted when there are periods of silence, nothing to transmit, no channel is held up for a communication, and what do you think the other advantage is? A general question. So, why is the VoIP so cheap?
Bandwidth requirement for transmission will be small.
Why is that? Why bandwidth requirement is small?
Since you can transmit more data over. You don't have to transmit throughout continuously.
That's what we are saying, that the channel is shared. When there are no data to transmit, don't transmit. That time the other
people can transmit.
People can transmit. It's one reason. Are there any other reasons? I mean, just see that the cost of the telephony has just dropped drastically. So, one of the main reason is this packet switched transmission. VoIP costs nothing, no? You know that. Only the cost for a broadband service or something. So, just think of it, because it is not pertain to our course really. So, just think of it. There are many other reasons why the cost has come down. Okay. So, let us proceed. A variable bit rate traffic, fixed size packets are generated or nothing is generated at all. So, this is one type of VVA traffic. We were discussing a general concept of a VVA traffic, where the size of the data was varying, and that too they were generated at random times. Another category of traffic you will find in the network is the sporadic traffic, where packets are generated in bursts and then there are periods of silence.
But it looks similar to the previous.
Okay, I think this diagram is a bit inappropriate here. Actually, we should have long periods of silence and the data size also should vary. Yeah, this diagram is inappropriate here. Okay, I think I will have another example here. So, that data, the example there is not appropriate. So, one example of a sporadic traffic is a fire alarm, where very rarely a fire condition is detected, but once it is detected, large number of alarm commands are sent out. There are response messages from these, and maybe action to be taken by sprinklers and so on. So, suddenly there is a peak load, suddenly the load increases due to alarms, called a alarm avalanche. So, you would get a scenario like this, that suddenly there is periods of silence and suddenly you have a burst of traffic occurring, the alarm avalanche. So, this should be the appropriate example for a sporadic traffic and not the other one. So, that was by mistake got inserted there. Now, let us see what are the choices of networks for real time applications.
So, this sporadic traffic can be a special case of variable bit rate, means where there is periods of silence are very long.
Okay. Okay. So, the sporadic traffic and the variable bit rate traffic, there are many similarities between them, but possibly what we can say is that for a sporadic traffic, we are sure that once there is a burst, another burst will not occur immediately, whereas a sporadic, it can be even occurring throughout. I mean, even the channel can be held up for the maximum size that can be generated, maybe they can get generated continuously. But here for a sporadic, it is a burst, and once it occurs, we know that it will not occur immediately. So, there is a difference, minor difference between a sporadic and a variable bit rate traffic. As we were discussing to start with, real time applications are becoming spread out geographically, because the data sources are located at different places, the sensor are placed in different locations, and also even when they are not geographically spread out, there may be components which are located in an enclosure. For example, let us say a car. or a room that is automated or something. So, even though they may not be geographically spread out, but there will be various components in an enclosure which need to communicate. So, there are two scenarios here that we will be addressing. One is geographically spread out, and another is they are located almost the same enclosure, different components communicate. There are many examples of such applications. Automated manufacturing systems, we had discussed about this, high speed data acquisition systems and so on. Now, when they are not really spread out over a very large area, which is normally the case, they are spread over a limited area, local area networks are an automatic choice for networking. In older times, there used to be point to point links and circuit switching. These were popular. When different components need to communicate, used to have either connect them point to point or use circuit switching. They are inefficient and costly. Why is that? Why is point to point links and circuit switching inefficient and costly?
Because there can be variable traffic. Medium only bigger.
Okay, yeah, exactly. So, there are many reasons. If for point to point, we will see that there are many disadvantages, and even for a circuit switched, whenever a connection is set up, the entire bandwidth is reserved for it, I mean the allocated bandwidth, even though it may not use that. So, it is inefficient. Let us see the problems with circuit switched network. A fixed portion of bandwidth is reserved based on the peak demand, and if the bandwidth requirement is constant, then circuit switched network is all right, but that is rarely the case. Very rarely you will find that no, the data is entirely constant, and many times the data is burst in nature. Similarly, with point to point networking, there are problems. One of the main problem is that the number of wire segments increases exponentially with the number of units. So, if there are n units to be connected by point to point wiring, the number of wire segments you will require is n minus 1 to the power n. Do you agree with this? Why is n minus 1 to the power n? Yeah. So, each component needs to be connected with a wire to n minus 1 other units, and there are n such units. So, n minus 1 into n minus 1 n such multiplications, which leads to n minus 1 to the power n number of wires. Just see, it has risen exponentially, and that too really fast. And when the number of component increases, that is complex systems, as the systems are nowadays, the complexity of the wiring becomes enormous, and naturally reliability drops. Some wire has become loose, wire is cut, and it looks like a mess of wires, and if somewhere there is a problem, it becomes very difficult to detect which wire has snapped or is loose. And not only that, it has low reliability and maintenance is a problem, but also the cost of wires is a matter of concern. You have to put so many wires and connect them, and also the weight of these wires becomes very significant, and we are talking of embedded applications and inside one enclosure and so on, and it becomes very difficult to continue with point to point wiring. In embedded applications, one type of network that evolved was the controller area networks, or CAN, which we will discuss briefly, and then LANs are very popular, And then of course, internet as an example of a wide area network is also.
Real-time systems of the internet.
Yes, we are discussing about bank transactions, isn't it? They will occur on internet, or even you want to control some sensors on the internet from different places, it is possible. So, internet is also used heavily in setting up real time communication. First, let us look at the controller area network. Initially created by the automotive supplier Bosch, a German manufacturer of automotive components in mid 80s, so about 25 years back. So, the goal was to reduce wiring harness weight and complexity. So, wiring harness is the set of all the wires that are being used, and as the number of components were increasing, the manufacturers were observing that the weight is becoming enormous and the complexity of wiring is also becoming very bad, resulting in low reliability, as we were discussing just few minutes back. So, the CAN evolved and is heavily used to connect components of a embedded controller, and nowadays not restricted to automotive segment alone, used in various other places. For example, a SIP or maybe some embedded avionics and so on. The end-to-end length of a CAN is less than 50 meters, because these work in small enclosures, and as a result the propagation time of a CAN bus is very small. I think yesterday we were just mentioning that the propagation time of electromagnetic signals is 1 kilometer per 5 microseconds or something, some data we are mentioning. So, for 50 meters the transmission time will be in nanoseconds, right. So, when the transmission time on the bus is nanoseconds, it is more like a local bus in a computer. Now, let us just take try to understand CAN through an example of an automotive application. The present day automotive electronics is sophisticated. For example, a car on the road will have dozens of processors there called as ECUs, electronic control units. So, they control various aspects of a car. For example, there may be ECU for engine management, for fuel injection, and this has become now compulsory for all cars to have automated fuel injection controlled by a processor. Active suspension, braking, lighting, air conditioning, security, central locking, all these are controlled by electronic components and which are need to communicate with each other, and they are interconnected using a CAN bus. When the engine is operational, lot of information is exchanged among these various ECUs. But in the older cars, before let us say 20-25 years back, there were electric components and there were some electronic components, meters and so on, but they were interconnected using point to point wiring. So, this was the evolution from the electrical wiring, generator, light, battery, ignition and so on. So, in the similar way, the electronic components were also interconnected using a point to point wiring, and as the complexity of the cars, number of electronic components increased, the length of the wire was astounding. Even that time, in good models of cars, you would need several kilometers of wiring. It adds to the cost of manufacturing, the weight of the wires is significant. Just imagine 1 kilometer of wire, how much it will weigh, the complexity of wiring, and not only that, reduced reliability, because these different wire segments can become loose, can be cut, and so on. One of the special requirement at that time on CAN was handling of noise. Compared to the other types of buses, there is a special requirement of the CAN bus regarding noise, because the origin was in the automotive segment, and the automotive components are heavy producers of noise. For example, wherever there is a motor, there are sparks and large noise is generated. Any motor you can easily make out by the noise it produces. You just take a radio system there, you can hear the noise that it produces. Even the ignition system, RF transmission, all of them are heavy producers of noise. Another requirement was for it to operate at 12-volt power supply, because all automotive vehicles operate at 12-volt supply. And one thing that is important here is that it specifies the physical and data link layer, and leaves the higher layers to the implementer and gives flexibility. And the MAC protocol is that makes sense. MAC protocol, the medium access control protocol, is the CSMA/CD. CSMA/CD, you know from a first course in networking. One implementation of the CSMA/CD is the Ethernet, which is very popular in traditional networking. So, CAN-MAC protocol is also CSMA/CD. And here, when CSMA/CD is used, how do you assign priorities to different sources? Because there are some components whose messages need to be transmitted without delay, whereas there are other sources whose data can wait a little bit without much problem. And the collision CSMA/CD protocol, an implementation of this, the Ethernet, I mean, we were just mentioning that it treats all the data sources as the same. So, how does this assign priorities to messages? What it does is, each outgoing message is given a priority. The different sources, basically, they will have priorities assigned, and these are unique. So, predefined priorities are assigned to sources. And when there are simultaneous transmission requests, the protocol that is used here is called as a non-destructive bitwise arbitration method. In a collision based protocol like Ethernet, you know that when a collision occurs, needs to be retransmitted, isn't it? So, they keep on trying after exponential back off. So, that is from a traditional from a first level networking course, you know that. But here it is a non-destructive bitwise arbitration, because even when there are multiple sources trying to transmit, there is no necessity of a repeated transmission. It is non-destructive. Even though collision is detected, need not be any retransmission. Let us see.
The non-destructive bitwise.
Yeah, we will see what is meant by bitwise. We will see that the unique IDs or the priorities of the sources, they are transmitted bitwise, right, and based on the priorities of different sources that are trying to send at the same time, the examination of the bits leads to identifying which is the one that needs to transmit. That is the arbitration mechanism. So, let us look at this, how it works. So, the priorities of the transmitters are considered in this, the non-destructive bitwise arbitration, and as is a CSMA-CD protocol, it is a broadcast mode of transmission, 1 Mbps transmission speed, and I think later 2.0 it has the transmission speed has increased to 10 Mbps. So, this is the basic mechanism which is used to resolve a contention. Just see here, there are two nodes and they transmit their ID at the start. Okay. Of course, we are trying to explain it in a very simplified way. It need not be that it always starts with a ID, it may be some headers or something, but at certain point of time the IDs need to be, the IDs are transmitted, and these are 0 1, and let us say the resolution mechanism is that, see, this is one resolution mechanism that we are discussing. There can be a dual of this, I will just explain that. See here, once the ID is started to be transmitted, see here, node B has put its 0 here, the most significant bit, and this also has put 0 here, node A, and on the bus 0 is transmitted, and they can hear that they have transmitted 0, and 0 is actually getting transmitted, and now both A and B transmit 1, and they could hear that 1 is also getting transmitted. But at this point node A is transmitting 0 and node B is transmitting 1, but 0 is getting transmitted. Okay. So, what it means is that a lower number, lower priority number, priority 1 is higher priority than priority 10 or priority 20. But if it was the other way around, that priority 20 is a higher priority than priority 2 or something, then when a 1 is transmitted, it will transmit 1 on the bus, right. And once it hears that what it transmitted is different from what is actually what it shown on the bus is different, then it will just drop out, it will not transmit. So, I think some other part of the example I think forgot to give there, but that is the basic idea.
After that drop out, it will again retransmit or not? Or
it will drop out, it knows that a higher priority message is getting transmitted, it will wait according to the CSMA CD, it will wait for certain time, let the higher priority message pass through, then it will sense the channel and see whether it is idle, and if it is idle, it will again attempt to send, and again this arbitration will take place, that whether there is a higher priority message also waiting to be transmitted, and it will get its chance to transmit at certain time. Is that okay? Okay.
this may cause starvation and all. Like not starvation, what do you call?
Undue delay for some, is it? Yes, see, the way the components are designed in a automotive application or any other embedded application where time matters, these are designed conservatively, assuming taking the peak load into account, and normally it won't happen that a source never gets an opportunity to transmit. What might happen is it gets delayed, and the lowest priority messages will anyway, messages such as logging and so on, which even if delayed by some time does not matter.
But there may be some critical thing also, because it is a real time application.
Yeah, that would depend on the design actually. That would, yes, if the design is not proper, there can be problem,
has
that
to
some
be
critical message also can get delayed, but normally we will lot of simulation and so on would have gone before the parameters are fixed.
So that has to be taken care by the designer.
Definitely,
Protocol
yes,
doesn't.
yes. The critical messages are not delayed, that has to be taken care during the design period, and we will just examine that a theoretical analysis in the term of RMA or EDF similar to that would be difficult here. We will just identify the reasons. So, a theoretical analysis, whether given the bandwidth and the protocol, whether the constraints of all the sources will be met, is difficult to analyze theoretically. We will identify the reasons, and that we will do later. So, let us proceed with our basic discussions now. Now, the kind of LAN topologies that are used in a real time application can be one of the following. We will see examples of this, and as we proceed further, maybe after 2 lectures or something, we will have a better idea about each of these topologies, how they are getting used and what are the issues involved. One is of course the bus, which we are familiar with the first level networking course. Tree configuration, star configuration, ring configuration, and wireless. So, these 5 are extremely popular, occur almost everywhere. So, let us check these out, some properties of this. The bus topology, as we know from a traditional networking course, first level networking course, is that there is a bus, typically a coax cable, and various types of computers attached to the bus, and then it is the bus is terminated, the terminators here in a coax cable. So, why there are terminators, etc. So, all those are first level course, let us not waste time on that. Since there is a single bus, the nodes that are connected to it contend for it, and they use a broadcast mode of communication. They used to be connected using a coax cable about 15 years back. The older networks LAN, you still find they were coax cables, and then there were the computers were connected using T-sept interface connectors, the BNC cables. So, it used to look something like this. Nowadays, rarely in a LAN you find this, and then terminating points were placed at each end of the network cable for load balancing. But now the scenario has changed. No one uses a coax cable, and the bus in the conventional sense is gone. Have you seen in the lab? They are not there, isn't it? So, what is the reason? Why is it that the coax cable vanished?
This cable may be lossy cable.
Coax cable has excellent electrical characteristics compared to the kind of cable that you see today in the lab.
Data rate may be slow.
The data rate was excellent on the coax cable. You know, in a coax cable, you have metal insulator on a cable to prevent noise. Electrical noise can't affect the signal because there is a sheathing, a metal sheathing on the wire. So, it will be, I mean, the signal characteristics, transmission characteristics are excellent. Noise is really low in those cables.
For normal purposes, such thing is not necessary. That level of
No, data transmission is very fast nowadays. You know, gigabit networks are there in the lab. I hope you.
Attach new mode station to this coaxial cable, then it will take more installation time. For the cable and attach new mode stations.
So, you are saying that attaching stations is difficult, is it? No, you have T sections available. Just put T sections. I mean, it's bit of work putting a T section and attaching a connection, but it can be done. It's not that it's that difficult. How is that? I mean, compared to what? What is the current networking? I mean, what is the kind of cable there in the lab? Okay. So, it is UTP. One advantage is the cost, and the signal transmission is excellent here, as you will see, because of various reasons, and at low cost. And not only that, the configuration of the network has changed. It has changed from a traditional bus to a star configuration. You see in the lab, see that all are connected in a star network, and the cable was very difficult to manipulate, bulky. You can't really bend it, conveniently attach it on a wall or something, right? But these are
soldered type, and then you should prone to that.
and not only yeah, and another thing is reliability. See, if there is a break, then the entire network will be down. But here in a star network, even if just one cable is broken, is out, then still it will operate satisfactorily. So, for those reasons, the coax cable in the typical lab scenario has vanished, replaced by universal twisted pair, a cable appearing like this, and RJ45 jacks, which typically you handle in the lab and attaching the network connections. But let us spend few minutes, because these are also important as we proceed, is how exactly, I mean, how does the computer connect to a network cable, and how does a computer, let us say we know that the physical address of a computer is unique and so on, but how does that happen, and how what about the protocol issues? How is the protocol issues handled in a computer? Anybody knows about that? How is the protocol, network protocol implemented in a computer?
So, we are attaching the interface card to the computer.
Okay, so this is the answer. There used to be a card like this, which used to fit into the motherboard, the NIC card, network interface card. It has a unique ID for the host. Basically, each of the NIC has a ID, which becomes the ID of the host, and the low level protocols are all coded in this. They handle about the collision resolution, arbitration, sensing the bus, all these are done by this here.
Coded means, sir, is it some kind of firmware?
You mean the ID is, how is the ID coded? ID coded is just a, I think 42-bit number, a binary number, 48-bit binary number, it is there. The protocols are there, we will just look at that. So, used to be like this, a special card used to get attached about 15 years back, but now since every computer is networked, see those days many people did not network their computer, they used to operate it standalone, but nowadays it is rare to find somebody operating a computer standalone, and since it is a requirement for every computer, every PC that is manufactured. So, this card is even built into the motherboard.
How does this code differ from IP address?
Okay, so again a very basic networking question, let us not spend time on that. See, the one is the physical address, which is given by the it's hard coded into the desktop or a computer, but there is another address, the IP address, which is given by the administrator. Okay. So, this address is bound to the IP address, and there are address resolution protocols and so on. Please refresh the first level knowledge, the physical address of a computer and its IP address. Okay. They are very different addresses. The physical address is hard coded, whereas the IP address is assigned. So, used to appear like this, that you have these coax cables, T connectors, and they are connected in the form of a bus, but nowadays that does not exist, right. Each of them is connected in a star connection. So, what is at the center of the star? Okay. So, there will be a switch or a hub which is at the center of the star, and the computers are connected in a star connection. That is how every lab will look like. The network interface card, I think it is much more intuitive to talk in terms of a card rather than some component on the motherboard. The network interface card, it takes care of transferring data at a specific rate, because you know there is a LAN speed. When you talk of a gigabit LAN or a 10 Mbps LAN, the data needs to be transferred at that rate, irrespective of the processor speed, or whether your computer, you have a old computer, fast computer, a slow computer, or you have a new faster computer. The data transmission on the network has to be at a standard speed, determined by what kind of network you are using, whether you are using a 1 Gbps Ethernet or you are using a 10 Mbps Ethernet. So, this is the card which takes care of that, transfers data the rate independent of the whether the computer is a old slow computer, it is a new fast computer, or in other words, the NIC, it shields the LAN from the characteristics of the device. The device may be slow, fast, whatever, but the transmission occurs at the required rate. The NIC is also known as a LAN adapter. It relieves from the computer, the CPU, from the electrical and low level networking issues. The protocol issues are all encoded in the NIC or the LAN adapter, also known as AKA, just written the short form, also known as a LAN adapter. Looks like this. This gets attached to the motherboard, and here your RJ45 cable gets attached here, and this is at the back side of the computer. And see these chips here, they would take care of the lower level protocol issues. The NIC directly accesses the computer's memory and transfers data using DMA. So, reads out data onto the network, reads in data from the network and so on using DMA, and takes care of parallel to serial conversion, because it connects to the PCI bus inside the computer, which is a parallel bus. So, this is also another responsibility of the NIC, in addition to taking the lower level protocol issues. It also uses DMA mode to transfer data and also convert data from serial to parallel. And nowadays you won't find a card if you look for it, because they are built into the motherboard. The tree topology is also popular when you have splitters and the different buses get arranged in the form of a tree. The star topology, as we were saying, is become present almost everywhere. Every lab, every LAN that you see around has a star topology. At the center may be a hub to which the different computers are attached. The wireless, even though we said a topology, it's not really a, doesn't denote a specific topology, because these are free to move. Nodes are free to move and they can take any shape, isn't it? But still it is I think from a classification point of view, we can consider wireless also as a topology. And there are several versions of IEEE 802.11 standard which define various forms of wireless LAN connections. So, maybe as we proceed slightly more in our discussion on using the wireless for real time communications, we will discuss these issues. The older networks used to appear like this. There is a bus and the computers are attached on that, and the present one looks like this. We had seen that it is much more reliable, it is cost effective. The twisted pair costs very less, 1/10 of the cost or maybe 1/20th of the cost of what the coax cables used to cost, can be easily manipulated and so on. You can set up a network in less than a few hundred, I mean 500 or so rupees. If you have a small set of computers using the hub, it costs some 200 rupees or something, 300 rupees, and then the wires cost almost nothing. You can set up a LAN even in your hostel rooms. Another one which is very popular in real time applications is the ring topology. So, the computers are connected in the form of a ring, and the individual computers are connected to the ring through a multi-station access unit or MSAU. MSAU can also be a hub. We will just see the diagram. In the ring topology, the nodes transmit in turn for a predetermined period of time. Because they take turns and also transmit for a predetermined period of time, therefore, when something needs to be transmitted, you know exactly how long it will take. I mean, in the worst case, depending on when the data has arrived, to the time the data would be, the transmission would be complete, it is very easy to compute the time it will take, isn't it? Because you would compute how much time each one will transmit, and it is in which number among all this. So, depending on how many are there before it and for how much they will transmit, you can find out when it will get its turn and for how long it will transmit, right? And based on that, you can find out the transmission time predictably. So, that is one of the main reasons why the ring topology is popular. But as we will see that the ring topology has its problems. We will identify the problems. Let us proceed. Because of its characteristic that transmission time is predictable, can compute a bound on the transmission time, it is popular real time applications. Would look like this: computers connected on a ring through MSAUs, which can be hubs. There are several problems with the ring architecture. One is that any break in the ring can bring the whole network down. One major problem, reliability issue. The other difficulty in using the ring architecture in real time embedded application is that is a poor fit to the linear topology in most of the assembly line and similar applications. So, naturally these are in the form of a bus or something rather than in a ring. Of course, we can have a token bus architecture where we have similar protocol like a ring, but we use the bus as the topology. It has benefits of both the bus and the ring architecture. The stations are logically arranged in the ring, and token is passed, and as long as a station or a computer holds the token, it can transmit data. So, the arbitration mechanism is taken care through a token, because at any time only one station will be holding a token, and once a station gets the token, it starts to transmit, but there are durations assigned for each node for how long they can transmit once they get token. After that time, even if they have data to transmit, they have to give the token to the next node. So, after transmitting its duration, assigned duration, it needs to pass the token to the neighbor, and the token propagates around the ring, and at any instant only there is one token holder who can transmit. So, arbitration mechanism is simple, collisions are prevented. And of course, we should have protocols for how to add and remove stations in a token bus architecture or in the logical ring, because there may be stations which are part of the ring at some time and they might get excluded in some other time. The other thing is that the physical and logical order of the stations may not be the same, and also all the stations on the bus need not be on the ring. So, it is just an I will just show you with an example, that even though there are many computers attached to a bus, all of them may not be on a ring. Just see here, this is not included in the ring, so they are on the bus. So,
then how will that communicate?
See, it does not participate in communicating with this using the token bus architecture.
Then normal bus topology only will use.
Yeah, exactly. So,
more than two logical link pursuit, those stations are not in that particular link. Can they form another link?
yes, why not? In a token bus, there can be on a single bus multiple rings can exist. So, let us not complicate the issue. Let us just understand the basic concept of a token bus, because we will discuss its use in real time application, the protocols that are used, we will do some performance computation for this, in what applications it can be used, for what it cannot be, and so on. We will discuss little later on. So, we will just stop here, and we will continue with few more basic issues before we start with the protocols for real time communications, which is suitable for which application and so on. Thank you.